4% growth repeats by multiplying by 1.04 each year.
Welcome to Hazel Growth Hollow. Take a moment to watch the scenery. The math here is built directly into the world, so we can see how the quantities behave before we even try to name them. As the squirrel moves along the paths, pay attention to the acorn piles. By tracking how these physical objects increase or decrease from one step to the next, we reveal the mathematical rules at play. When a quantity changes by the exact same percentage or multiplicative factor over equal intervals of time, we're looking at an exponential model. Exponential models record real-world patterns where the growth or shrink rate is permanently locked to a constant multiplier. This diagram mapped onto bark shows a scenario like a savings account that grows by 4% each year. You can see the acorn caches getting progressively larger, with that 4% rate etched next to every single step. Because the account changes by that identical percentage every year, we are repeatedly multiplying the current total by the same factor. That repeated multiplication is exactly what defines an exponential growth situation. Whenever growth relies on a percentage of the existing total, rather than a fixed number of added items, it operates as a multiplicative compounding process. Now, look at this mossy path diagram showing a seed trail that shrinks at each step. If a phone battery loses 15% of its charge each hour, we need to ask why this isn't considered a constant rate linear model. Watch the exact volume of seeds removed at each marker.
Losing 15% each hour is multiplicative decay, not constant subtraction.
The physical amount taken away gets smaller every hour because the 15% calculation depends on the current shrinking total. With the baseline constantly shrinking, that 15% reduction acts as a multiplicative change. We are not subtracting a fixed hourly amount. Since the subtracted portion adapts to the shrinking whole, it fails the test for a linear model. This is an exponential decay situation. Let's test this logic. If a population grows by 6% annually, what specific multiplicative factor should we use in an exponential model? Take a moment to think about it. Looking at this seedling ring diagram, we have to start by defining our baseline. Before any growth happens, the original population represents a full 100%. Next, we add our 6% increase to that original baseline. This brings our new total up to 106% of the original population. Finally, we convert that 106% into its decimal form, giving us a final growth factor of 1.06. Anchoring the rate of change to that 100% baseline is the necessary first step to constructing an accurate exponential multiplier. Matching the squirrel's path to the exact numbers and symbols in the scene confirms the mathematical relationship. The physical environment provides the evidence for the relationship, and the notation simply records what the world is already doing. Look at these final values. Ask yourself, which marks in the environment prove the mathematical relationship, and how does the animal's path make it true? Recognizing an exponential model is about observing when the quantities in the world are constantly multiplying, adapting, and compounding.
100% plus 6% is 106%, so the growth factor is 1.06.